Hey, welcome to today's video. I'm Prof. Omar. Today we're going to talk about the RSA encryption algorithm, and this is the end of a number theory part of the Discrete Math course on this playlist. So what we're going to talk about is the details of the mathematics behind this algorithm that's used in a lot of email subroutines to encrypt messages so that you can send messages between people and nobody can see what's going on. Okay, so the backbone then is the goal being sending messages secretly, so only the sender and the receiver know what the message that's being sent is. Okay, so imagine you had Bob, who has a bunch of different friends, and Bob wants a secure way of sending messages or receiving messages from these different friends. So you might have a friend like Alice, or Augusto, or Abhishek. Okay, and these messages are being sent to Bob over some kind of public channel. So they might be messages like text or email, and somebody could try to intercept them and try to figure out what those messages are. Okay, so what we're going to do is encode messages mathematically as numbers, and then use the numbers to actually encrypt them in a way that anybody who intercepts the message through some public channel that the message is being sent through can't understand what the message is actually saying. So we're going to start by using a cipher, meaning a way to turn words into numbers. And in this video, we're going to associate each letter of the alphabet with its position. So the letter A is going to be encoded as 0, 1, B as 0, 2, etc., Z or Z as 26. And then we need a way to introduce a blank, so we'll use 27. Okay, so for example, if you wanted to send the message, I want candy, you'd have something like 09 for the I, a 27 for the blank, right? And then 23 for the W, 01 for the A, etc. And so you'd have this long number here encoding exactly what your message is. Okay, so we'll assume a cap on the length of the message, let's say like 140 or 280 characters. You know, numbers that come randomly out of nowhere. And if that's the case, your messages have 280 characters. Each of them are encoded in 2-digit numbers. So the actual length of the number has at most 560 digits. So the first thing Bob is going to do is compute a number n, or select a number n, that's larger than the actual size of any of the numbers that encode messages. Since the messages have at most 560 digits in them, we'll let n be a number that's at least 10 to the 561, and then we're safe. Given that, what Bob will do is make n public, meaning he'll share what n is with everyone, and so everybody's going to have a process where they take their message and encrypt it, and is going to involve this number n. And then Bob is going to select n in sort of a very clever way for himself. He's going to select n to be the product of 2 primes, and these primes are going to be huge. Okay, so the reason to do this is P and Q are going to be really useful for Bob in the algorithm of encrypting, but Bob doesn't want people to know what P and Q are. And it's actually really difficult computationally to prime factor a number. So this is great for Bob keeping things a secret. And I'll say here, Bob keeps P and Q secret to himself. Now with that set up, if Alice wanted to send a message M, what should she do? Well, first of all, she's sending it over a public channel, so she wants to change M into something else, an encrypted message, so that people don't know what it is that she's actually sending. And this encrypted message is going to be an actual number. M itself is a number as well. We've taken our actual message, changed it into a number, and that number is being sent. So Alice is going to change this to something, and that's the thing that's going to get sent to Bob. So that if you have some person over here, say Eve L, who tries to intercept, Eve L will see C, which is going to be a bunch of gibberish. It may not even be able to be decoded using the cipher. So we're going to explain the process of how the number C, the jumbled up message, is actually created. And there are a couple of steps. So Bob first picks an integer E so that E is between 1 and phi of n. I'm going to talk about what phi of n is in a second. So that phi of n itself has a GCD of 1 with n. Okay, so this seems a little bit weird. So we should ask some questions. First of all, this number E has a special name. E is called the encryption key. Okay, so that's a good word to know. And then, what is phi of n? So phi of n is the number of integers in the list 1 through n whose GCD with n is 1. Okay, so in this particular situation, n is a product of two primes p and q. We can actually figure out what phi of n is. We're taking the numbers between 1 and n and figuring out which ones have no common factors with the number n, which is itself pq, right? So Bob can do this because he knows what p and q are. Okay, so we take the numbers between 1 and n. There's pq total numbers, right? We'll subtract the number of multiples of p. There's q of those. P, 2p, 3p, all the way to qp. And then we'll take away the multiples of q. That's q, 2q, 3q, all the way up to pq. So there's p of those. But there's one multiple of p that's also a multiple of q, that's pq. So we have to add back a 1. So this number is p minus 1. If we factor it, is p minus 1 times q minus 1. Okay, cool. So there's our phi of n that Bob can actually calculate. So now the question is, how do you actually find a number E that satisfies this? So to find E, there are a lot of things that you can do because phi of n is going to be this massive, massive, massive number. One thing that you could do is pick random values for E and then run the Euclidean algorithm to test whether or not the GCD of E with phi of n is going to be 1. And the Euclidean algorithm, as we argued in one of the earlier videos, runs really quickly. It's actually logarithmic in the number that you enter. Okay, so then Bob is going to share this encryption key with everyone. So he already makes n public, and so he announces n, and is going to announce this encryption key. So he sends this information publicly everywhere. It's a lot of public sharing. But the point is, he's done some work. He has an encryption key and n. N is a bound on the number, the size of messages that he can receive. And then E is this thing that he's going to send to everybody that he's working with. And he doesn't have to send this universally. He can do it, send a different E to each person every single time. That's probably smarter. But he sends this to everybody to use for the process of encryption. Okay, so now Alice has to actually do the encryption process. So how does Alice actually do this? Alice is going to make C a particular number between 0 and n and pick it to be the number so that C is congruent to, here's the original message, raised to the E, which is this encryption key that was sent by Bob, computing it modulo n. Okay, so this here is the encrypted version of M that's being sent through the public channel. Now you might wonder, why is this a good choice for sending through the channel? We're going to see why this is a good thing to send, because there's an interesting way for Bob to actually take this message, decode, and end up with the original message that we wanted to have in the first place. Okay, so some comments. Why isn't it the case that an adversary like Eve L can take C and somehow manipulate it to find out what E is? Right, so imagine C was something like 247. Okay, and you're wondering what M is. E is public information, so E might be something like 173, and N is also public information, so N might be like 2467. Right? And the question is, why can't you figure something like this out? Well, it turns out that this is very difficult to do computationally in number theory. If you're given a modular equation like this and you're wondering what M is very difficult to do in general. Okay, so that's sort of part of why this is a safe thing to do. We won't go into the details of why it's hard to do, but this is something that's sort of known in the literature. Okay, so now we're in the situation where Bob has received this jumbled up message C. And the question now is, what does Bob do with C? So C is sitting here, sending it over this public channel, right? And Eve L wants this. Okay, but as we argued right over here, it's difficult to actually figure out what this is, just knowing C. Okay, so Bob receives C and is going to do some work. He already knows what 5n is. Remember, that's PQ, right? He's, P minus 1 times Q minus 1, which he can compute because he knows what P and Q are. Okay, so he's going to compute an integer D between 1 and 5n so that E, the encryption key we had before, times D is congruent to 1 mod 5n. Okay, so this is known because it's public. This is known to Bob. So if we think about this, E and 5n are numbers that Bob knows. So Bob can figure out what D is by solving a linear congruence equation, which we talked about in the video linked right over here. Okay, so Bob solves a linear congruence equation to get this. Okay, I should mention some of the mathematics actually that goes into doing this. This requires computing m to the e mod n, which you can do by repeated multiplication of m, combined with using some of the tools that we talked about in modular arithmetic to actually reduce powers of m mod n. Okay, but now Bob can actually compute this D thing, and D has a name. D is called the decryption key. And then now Bob picks a number n so that n is congruent to C to the D mod n. So Bob is taking this jumbled up message C and raising it to a power and reducing that mod n. And the power that he's using is the power here, which is the decryption key that he computed. Now, again, this seems like a whole bunch of stuff, and it doesn't seem clear why something like this does anything for us. But the real magic here is it turns out that this number here is the original message M. It's not clear at all why this is the case, but this is exciting. Somehow, through this entire process where Alice changes her message to this decrypted message C, which is over here, and then Bob subsequently takes that and applies this decryption process, Bob will end up with a number n that actually is the original message M that Alice wanted to send in the first place. So the question is why? Why is this the case? So we have all this different data. Let's actually recap what all of this data is, and then analyze why it's the case that N and M actually have to be the same. Okay, so the data is, we have this number N, which is PQ, and P and Q are private to Bob. Only Bob knows these numbers. Okay, then an integer E is computed. E is called the encryption key, right? And this is computed by Bob and used by Alice. And then this D, the decryption key, is computed by Bob as well and used by Bob to actually do the decryption. Okay, then we computed these two things, C, which is M to the E mod N when reduced as much as possible. So this thing here, the number C, is the encrypted message that Alice sends Bob. And then N is the decrypted message. And the big claim here is that N is actually M. Now I want to review some of the things that actually go on when doing all of this computation because it's kind of fantastic. So we have the computation of 5N, the GCD computation, which actually involves the Euclidean algorithm by randomly choosing E's and trying to find one where you get a GCD of 1. We have a linear congruence equation, and then we also have exponentiating using modular arithmetic. So this is all stuff that we talked about in the number theory section. Okay, so let's give an attempt at a proof, which is going to turn out to be not a correct proof, but it's a good first try. Since both of these numbers, capital M and capital N, are both between 1 and little n, M equals N if they're congruent mod N. Right, so for example, if N was the number, it's not the case that N is this because N has to be very large, but if N was like 100, we have two numbers between 1 and 100, and we're saying they're the same mod 100, so they actually have to be the same because they're small numbers compared to 100. Okay, so we might think something like this. N is the number that we end up with, and that's congruent to C to the D, mod N. Okay, but C is itself congruent to M to the E, so this is congruent to M to the E to the D, mod N. Okay, but we know something about E to the D, or sorry, ED. We know that ED is congruent to 1 mod 5N. So from this third bullet, ED is 1 more than a multiple of 5N. Is 1 plus k times 5N for some k. Okay, so M to the E to the D, that's M to the ED, which is M to the 1 plus k times 5N, which can be rewritten as M times M to the phi of N raised to the k. And now we might conclude then by Euler's theorem, which we talked about in the video right over here, means this thing here is congruent to 1 mod N. And so the expression we have here is congruent to 1 times M times 1 to the k mod N, which is congruent to 1 mod N, and we're happy. So notice this is combining a whole bunch of different things from the number theory section of this course. The one tricky part about this, though, is there's something wrong with it, which is that we can't necessarily use Euler's theorem. Euler's theorem requires that the GCD of capital M and phi of N is 1. little n is 1, and we don't actually know that's the case. So good attempt, but GCD of m and n might not be 1. So can't appeal to Euler's theorem. So we need to do something a little bit different. Okay, so what's the fix? What we'll do is we will prove two other things. The first is that m is congruent to n mod p, and then that m is congruent to n mod q. Okay, if that's the case, then the first condition says that p divides m minus n. The second one says that q divides m minus n. So this would mean that pq divides m minus n. Or in other words, m is congruent to n mod pq. And pq itself actually is the number n, so we're in good shape if we can do this. Okay, so let's actually try that then. Why would m be congruent to n mod p? Okay, so there's two situations. If m itself is congruent to 0 mod p, then n, which is congruent to c to the d, and that's m to the e to the d, so this is m to the ed, is going to be congruent to 0 as well. Okay, so that takes care of that. Okay, so if m is not congruent to 0 mod p, then we're in good shape because p is prime. In this case, the GCD then of m and p is 1, so we can use Euler's theorem in the prime case, which means so m to the p minus 1 is congruent to 1 mod p. Euler's theorem in the prime case is called Fermat's little theorem, and we have a video on that right over here. So using that, we get that n now again is c to the d, which is m to the ed. Okay, and now ed is just like we had over here, 1 plus a multiple of p, p minus 1. So it's 1 times a multiple of 1 plus a multiple of p minus 1. And so this is congruent to m times m to the p minus 1 to the k. And now we're actually in a situation, because the GCD of m and p is 1, to use Fermat's little theorem, or in other words, Euler's theorem in the prime case. This is congruent to this, which is then congruent to m mod p. Okay, so that takes care of this first bullet. And the second bullet is actually exactly the same, where we interchange the roles of p and q. So the second bullet is same as this first bullet proof. Okay, cool. So this actually does work. We actually get for sure that the message that we have at the end of all of this, the message m, is the message, or at capital N, is the message that we started with. And it's very hard to break the algorithm along the way, because it's hard to figure out what m originally was by just knowing C. Great, so that wraps up this video, and then in the next video we're going to see an actual example where we go through the process of encoding, encrypting, and decrypting, so we see the entire process and the entire flow. So I hope you enjoyed today's video. If you did, definitely click the like button, and if you want to see more videos like this, definitely subscribe to the channel.